High above the Earth, in the cold black of space, silence is perfect. The air is gone, pressure falls away, and with it all sound vanishes. From this vantage point, the Earth below glows with a soft blue haze. The moon hovers in the distance, locked in orbit, and beyond them, stars scatter the sky like dust across black velvet, distant, ancient, unyielding. For centuries, the cosmos appeared still and orderly. It moved, yes, but predictably. The planets traced their paths around the sun with a kind of mathematical grace. Objects fell, pendulums swung, tides rose, all according to the same invisible hand. That hand was called gravity, and for nearly 300 years its rules were written by Isaac Newton. In his Philosophiae Naturalis Principia Mathematica, published in 1687, Newton described gravity as a force, an attraction between any two masses. He gave it a simple, powerful formula. The gravitational force between two bodies, Newton said, is equal to the product of their masses, multiplied by a universal constant and divided by the square of the distance between them. This law was astonishingly accurate. With it, Newton could explain the fall of an apple, the orbit of the moon, and even the paths of comets from the far reaches of the solar system. It became one of the great pillars of physics. But even in its success, something about Newton's law was incomplete. He never explained how gravity worked, only what it did. How did the Earth know the sun was there? How could one object reach out across empty space and pull on another, instantly and invisibly? Newton himself admitted that this action at a distance, as he called it, was so great an absurdity that he would not presume to offer a mechanism. Centuries passed, and the question remained open. By the early 20th century, physics was beginning to change. Light, electricity, and magnetism had all been unified by James Clerk Maxwell into a single theory of electromagnetism. But there was a problem. Maxwell's equations said that light traveled at a fixed speed, about 186,000 miles per second, regardless of the motion of the observer. But Newtonian physics insisted that speeds should add and subtract. If a train moves forward and a light shines from it, shouldn't the speed of that light appear different to someone standing outside the train? Experiments showed it did not. This contradiction puzzled physicists, until a young man working in a Swiss patent office offered a new idea: Albert Einstein. In 1905, Einstein published the special theory of relativity. It proposed two fundamental principles. First, that the laws of physics are the same for all observers as long as they are not accelerating. And second, that the speed of light is constant in all frames of reference, no matter how fast the observer is moving. These two simple ideas led to stunning consequences. Time, Einstein showed, is not absolute. It flows at different rates for different observers. A moving clock ticks more slowly than one at rest. Lengths contract. Simultaneity, the idea that two events can happen at the same time, becomes relative. Einstein had shown that space and time were not separate entities. They were part of the same fabric, spacetime. But special relativity had limits. It applied only to observers in uniform motion, those not speeding up or slowing down. It said nothing about gravity. It could not explain why planets curved through space or why objects fell. Einstein knew that to understand gravity he had to go deeper, and in doing so he would rewrite the structure of the universe. At its core, the mystery of gravity lies in a single question. What is it, really? Is it a force, as Newton claimed, or is it something more fundamental, something embedded in the very geometry of the cosmos? Einstein began with a simple, yet profound observation. Imagine standing inside a sealed elevator in deep space, far from any planet or star. If the elevator begins to accelerate upward, your feet press against the floor. You feel weight. If you drop a ball, it falls to the floor. Now imagine the elevator is instead sitting on the surface of the Earth. The experience is identical. The pressure on your feet, the way the ball falls, it's all the same. Einstein realized there is no way to tell from inside the elevator whether the force you feel comes from gravity or from acceleration. This became the equivalence principle, the foundation of general relativity. In simple terms, it states, Being in a gravitational field is locally indistinguishable from being in an accelerating frame. This idea was the key. If gravity and acceleration are equivalent, then perhaps gravity is not a force at all. Perhaps it is the result of motion through curved spacetime. If acceleration affects how we experience space and time, and gravity is equivalent to acceleration, then gravity must also affect space and time. This was the crack in the wall. Through it, Einstein began to glimpse a new universe. To describe this vision, Einstein needed a new language, one that could express curves and distortions, not just forces. That language was geometry. With help from his former classmate, Marcel Grossmann, Einstein turned to Riemannian geometry, a mathematical framework designed to handle curved surfaces. Originally, it was developed to understand the shape of two-dimensional surfaces, like a sphere or a saddle. Einstein extended it to 4 dimensions, 3 of space and 1 of time. In this new picture, gravity was not a pull between objects. It was the bending of space-time caused by mass and energy. Objects like the Earth or the Sun warp the fabric of space-time around them, and other objects move along the curves created by that warping. In Newton's theory, the Earth orbits the Sun because it is pulled toward it. In Einstein's theory, the Earth orbits the Sun because the Sun curves the space around it, and the Earth is simply following the straightest possible path in that curved space. This is why astronauts in orbit feel weightless. They are not beyond gravity. They are falling freely, moving along a curved path in space-time, just as Einstein predicted. Einstein worked for nearly a decade to find the exact mathematical expression of his theory. In 1915, he succeeded. The result was a set of equations that describe how matter and energy shape the geometry of space-time, and how that geometry in turn tells matter how to move. These are the Einstein field equations. Spoken aloud, their essence can be expressed like this. The curvature of space-time, described by a geometric object called the Einstein tensor, plus a term involving the cosmological constant, is equal to 8 pi, multiplied by the gravitational constant, divided by the speed of light to the 4th power, or multiplied by the stress-energy tensor, which represents matter and energy. In short, geometry on the left equals energy on the right. Matter tells space-time how to curve. Space-time tells matter how to move. This elegant balance between what exists and where it exists is the core of general relativity. Chapter 2. The equivalence of falling and floating. In a modest room at the Swiss Patent Office in Bern, a man in his late 20s sits quietly at his desk, sifting through designs of electrical circuits and mechanical devices submitted by inventors. On the surface, Albert Einstein was a clerk reviewing technical claims, but in his mind he was reshaping the very structure of reality. It was 1907 when Einstein had what he would later describe as the happiest thought of my life. He imagined a man falling freely, perhaps from a rooftop or in an enclosed elevator, and noticed something peculiar in that imagined scenario. If a man is falling, and if the fall is unimpeded, he feels no weight. He does not feel pressed against the floor of the elevator. If he lets go of an object, it hovers beside him. To the man, it seems as if gravity has vanished entirely. From inside, the elevator is a perfect little universe where nothing seems to fall. Einstein realized there is no observable difference between free fall and weightlessness. And this insight, so simple in form, would become the foundation of his grand theory of gravity. This is known as the equivalence principle, and it is the cornerstone of general relativity. What falling reveals. To most people, falling feels like being pulled by gravity, by the Earth, by some invisible force. But Einstein turned this intuition on its head. He saw that falling is not the experience of force, it is the absence of it. When you are freely falling, you are not being pushed or pulled by anything. You are simply following your natural motion. What we feel as gravity when we stand on the ground is actually a resistance to falling, the floor pushing up against our feet, keeping us from following the path that space and time want us to take. In this way, standing still is actually being accelerated. Falling is not being pulled, it's being allowed to move freely. This idea seems to contradict our everyday experience, but it explains why astronauts orbiting Earth feel weightless. They're not outside Earth's gravity, they're inside it, but in a constant state of free fall, moving forward fast enough to fall around the Earth rather than down to it. They feel no gravity because they are not resisting it. Einstein's principle asserts that the effects of gravity and the effects of acceleration are locally indistinguishable. In a small, enclosed space, like the elevator in his thought experiment, no test you perform can tell whether you're in a gravitational field or accelerating through empty space. The shift in perspective. Before this revelation, gravity had been understood as a force, a kind of cosmic magnetism pulling masses together. Newton had codified this view, stating that every mass in the universe attracts every other with a force proportional to their masses and inversely proportional to the square of the distance between them. But Einstein was beginning to suspect something far more subtle. He saw that the laws of nature do not distinguish between being pulled by gravity and being pushed by acceleration. To physics, the two are equivalent. That equivalence suggested something profound. Gravity may not be a force at all. It may simply be a consequence of how space and time behave near mass. If you can mimic gravity simply by accelerating, then perhaps gravity is not a thing acting upon you. Perhaps it's the geometry of your surroundings dictating your motion. This changed the direction of Einstein's work completely. Rather than trying to improve Newton's force law, he sought a deeper answer. What if mass bends the structure of spacetime itself? And what if the motion we interpret as falling is just an object traveling along the contours of that curved space and time? The elevator and the beam of light. Einstein returned to the elevator again, adding a new twist. Imagine now that a beam of light passes through a hole in the elevator wall, just as the elevator begins to accelerate upward. From the outside, we know the light travels in a straight line. But inside the elevator, the floor rises to meet the beam. To an observer within the elevator, the light appears to bend. If acceleration is indistinguishable from gravity, then this must mean that gravity bends light. This was revolutionary. In Newton's theory, light shouldn't be affected by gravity. It has no mass. Yet Einstein now predicted that gravity changes the very path of light, not by pulling on it like a force, but by bending the spacetime through which light moves. This was more than a mental trick. It was a bold, testable prediction, one that would later be confirmed by astronomers during a total solar eclipse. But in 1907, it was still just a daring consequence of Einstein's new vision. Stretching, squeezing, and tides. Another real-world effect of gravity hinted at this new geometry: tides. Tides occur because different parts of the Earth feel slightly different gravitational pulls from the Moon. The side of Earth closer to the Moon is pulled slightly more than the far side. This differential force causes oceans to bulge outward in two directions. In Newtonian gravity, this is explained as the difference in gravitational force at different distances. But in Einstein's language, tides are a sign that spacetime is curved. Two objects falling side by side in a curved spacetime don't always stay side by side. Their paths, even though each follows a natural, force-free trajectory, may slowly drift together or apart. This is the essence of tidal gravity, a difference not in force, but in how space and time themselves are stretched near massive objects. Such effects are small near Earth, but near extreme masses, like black holes or neutron stars, the curvature becomes so strong that objects are torn apart. This is no longer gravity in the traditional sense. It's the warping of reality itself, from falling to geometry. The equivalence principle didn't just explain falling. It forced a fundamental rethinking of physics. Einstein was now convinced that to understand gravity, he had to stop thinking of it as a force. Instead, he needed a new kind of physics, one that could describe curved spaces and how objects move within them. He turned to the mathematics of curved surfaces, a branch of geometry that had once seemed abstract and useless, now revealed as the key to the cosmos. Over the next few years, Einstein would immerse himself in this new geometry. He would learn how to describe distances and times not on a flat stage, but in a dynamic, warped arena, a four-dimensional fabric called spacetime. And that fabric, he would find, is sculpted by the presence of mass and energy. The horizon ahead. The equivalence principle didn't just raise a question, it opened a path. It led Einstein away from the idea of gravity as an invisible force and towards something more elegant and radical. That what we call gravity is just the expression of how mass shapes the landscape of space and time. This was no longer a physics of attraction, it was a physics of motion through a curved world. And so the next step was inevitable. Einstein had to find a way to describe that curvature, to give mathematical form to the bends and twists of spacetime, and to show how those bends cause objects to move. What began as a simple thought, a man floating in an elevator, would now lead to the most beautiful equation in physics and a new theory of the universe. Chapter 3. The shape of spacetime. With the equivalence principle in place, Einstein now faced a daunting challenge: how to describe gravity not as a force but as curvature, a bending of space and time themselves. This chapter explores the central idea of general relativity, that matter tells spacetime how to curve, and curved spacetime tells matter how to move. But to understand that, we must first grasp what it means for spacetime to have a shape, and how that shape affects everything that moves within it. What it means for spacetime to be curved. Curvature isn't something visible in the usual sense. It doesn't mean that space has bumps or ridges like a terrain. Instead, it means that the rules for measuring distance and time change depending on where you are and how you're moving. In flat spacetime, the shortest distance between 2 points is a straight line. But in curved spacetime, the shortest path becomes a geodesic, which may appear curved when mapped out, but is locally the straightest possible route. Spacetime curvature reveals itself through behavior. You see it when light fails to travel in a straight line near massive bodies. Time ticks at different rates depending on altitude. Planetary orbits gradually twist over time. These aren't oddities. They are consequences of geometry itself being reshaped by mass and energy. In curved spacetime, what we once called falling is simply an object following a geodesic. It's not being pushed or pulled. It's moving along the straightest possible path available in a warped geometry. Just as a train follows its rails, a free-falling object follows the path laid down by spacetime curvature. This marks a profound shift from Newton's perspective. Newton taught that motion changes only when acted upon by a force. But Einstein proposed that motion appears to change because the stage itself, spacetime, is bent. This is why objects accelerate toward Earth, not because Earth reaches out to pull them, but because Earth curves the spacetime around it, and that curvature guides the motion of everything nearby. What shapes the curvature? The presence of mass and energy bends spacetime. But it's not just mass. Any form of energy contributes. Radiation, pressure, momentum, even physical tension. All these elements influence how spacetime curves. A small, compact object like a bowling ball creates a gentle dimple in spacetime. A star like the sun makes a deeper, broader well. A black hole forms an abyss, a region where curvature becomes so extreme that not even light can escape. In general relativity, the shape of spacetime is directly determined by how energy is distributed. The more concentrated the energy, the more intense the curvature. This insight leads to the core of general relativity, a set of equations that link matter and energy to the geometry of spacetime. Though complex and challenging to solve, these equations allow us, in principle, to calculate how any configuration of energy and mass warps the universe around it. Motion without force. Once spacetime is curved, it becomes the blueprint for how everything moves, from falling apples to beams of light. Objects no longer need a force to change direction. Their paths shift simply because the space they move through is bent. In this view, gravity is not a pull. It's a tilt in the very structure of reality. This explains the bending of starlight near the sun. The light always travels in a straight line, but the space it passes through is curved. From a distance, its path appears bent, not because it was tugged or slowed, but because the geometry led it that way. The same holds for planets. Mercury's orbit doesn't return to the same point each time, it precesses. Newtonian gravity couldn't fully explain this. General relativity does, attributing it to the subtle warping of spacetime by the sun's mass. A new kind of gravity. In Einstein's picture, gravity isn't just another force, it's the arena in which all forces play out. The electromagnetic field, for example, exists within spacetime, and when that spacetime is curved, the field behaves differently. So do particles, so do clocks, so does light itself. Curved spacetime influences everything, everywhere, all the time. This idea extends far beyond orbiting planets. It predicts time slows down near massive bodies. Light shifts in frequency as it escapes gravitational fields. Space itself can stretch, contract, and ripple, as in gravitational waves. Einstein had transformed gravity from a force into a question of geometry, and by doing so he not only explained what Newton could not, he revealed that space and time are active, dynamic elements of the universe. Now that the physical meaning of curved spacetime was in place, Einstein needed a way to describe that curvature in precise terms, and to link it mathematically to matter and energy. This called for new mathematical tools. Geometry had to be expanded into 4 dimensions, distances had to be redefined, and spacetime itself had to be treated as a flexible, deformable fabric. Einstein turned to the mathematics of differential geometry, where curvature isn't just a picture, it's a measurable, computable property built into the equations of motion themselves. That journey, from intuition to exact expression, would lead to Einstein's field equations, the beating heart of general relativity. Chapter 4, the field equations. By 1915, Einstein had the conceptual foundation in place. Gravity is the manifestation of spacetime curvature. The next step was to express that curvature and its relation to matter mathematically. The result was a single, compact set of equations, but behind them lay years of effort, an entirely new kind of geometry, and a fundamental shift in how we describe the universe. Describing curvature with mathematics. To describe how spacetime bends, Einstein needed mathematics capable of handling smooth, flexible surfaces in 4 dimensions. For this he turned to Riemannian geometry, developed decades earlier by Bernhard Riemann, a framework built to measure curvature from within, without needing an external reference. In this language, curvature is not about shapes you can see, but about how distances, angles, and trajectories behave in the presence of distortion. The key object here is something called the metric, a mathematical structure that defines how distances and times are measured in a given spacetime. Once you know the metric, you can calculate everything else: how particles move, how light travels, how time flows. But how does mass and energy determine that metric? That was the puzzle Einstein needed to solve. The core idea. Einstein proposed this: the curvature of spacetime at a point is directly related to the amount and type of matter and energy present at that point. In his field equations, this relationship takes the form of 2 sides. One side represents the geometry, how spacetime is curved. The other side represents the source, the energy, momentum, and stress from matter and radiation. The equation balances these 2. Matter tells spacetime how to curve, spacetime curvature tells matter how to move. What makes this revolutionary is that the geometry itself responds to what's present. Unlike Newton's fixed passive space, Einstein's spacetime is dynamic. It bends, stretches, and evolves in response to what it contains. What the equations do. Einstein's field equations are not a single formula, but a system of equations that apply at every point in spacetime. Given a distribution of mass and energy, the equations allow you to compute the structure of spacetime, how space is shaped, how time flows, and how objects will move. Conversely, if you know how spacetime is curved in a region, you can infer the mass and energy responsible for that curvature. These equations are incredibly general. They apply to stars and galaxies, to black holes and gravitational waves, to the entire universe as a whole. They contain Newton's law of gravity as a special case, When the curvature is weak and speeds are low, Einstein's equations reduce to Newton's familiar force law. But they also go far beyond it, predicting phenomena Newton could never have imagined. The challenge of solving them. Einstein's field equations are elegant in form but notoriously hard to solve. They are non-linear, meaning that the curvature created by one source affects the curvature created by another in complex ways. The geometry can fold back on itself, influence time, and ripple outward, making the equations difficult to untangle. In most real-world cases, exact solutions are impossible. But certain idealized cases, such as a static spherical mass, allow for precise solutions. The first and most famous came from Carl Schwarzschild, who found the exact spacetime geometry around a non-rotating star or black hole. This solution showed, mathematically and unambiguously, that black holes are not speculative. They are a natural outcome of Einstein's theory. Other solutions described expanding universes, oscillating stars, and even gravitational waves. Gravity becomes universal. Einstein's field equations don't just govern gravity, they govern the shape of reality. They apply to every part of the universe, from atomic nuclei to galaxy clusters, because they describe how energy in any form bends the fabric of spacetime. They also erase the boundary between geometry and physics. In general relativity, the laws of nature are embedded in the structure of spacetime itself. There is no separate stage on which events play out. The stage is part of the drama. This changes how we understand causality, simultaneity, even the limits of observation. It makes time local, distance relative, and the universe a participant in its own evolution. Chapter 5: The Black Hole Solution. In the wake of Einstein's field equations, the next major breakthrough came from German physicist Carl Schwarzschild. In 1916, he discovered a solution to those equations that described the spacetime surrounding a spherically symmetric, non-rotating mass, essentially a point mass or a static star. This solution, known as the Schwarzschild solution, revealed a new and astonishing phenomenon: black holes. The birth of the black hole. Schwarzschild's equation showed that spacetime can curve so intensely around a mass that there exists a critical radius, the Schwarzschild radius, where the curvature becomes infinite. This boundary is called the event horizon. It marks the point beyond which nothing, not even light, can escape the gravitational grip of the mass, the defining feature of what we now call a black hole. At the event horizon, the escape velocity required to break free exceeds the speed of light. And since nothing can travel faster than light, anything that crosses this boundary is trapped forever. No signal, no information can get out. At the very center lies the singularity, a point of infinite density where space-time curvature becomes infinite and the known laws of physics break down. The mystery of the singularity. Though the Schwarzschild solution offered a precise mathematical description of a black hole, it also revealed a profound mystery. The singularity at its core signifies a collapse of our current understanding. At that point, gravitational forces are so extreme that the equations we rely on cease to apply. According to the math, any matter that falls into a black hole is compressed to infinite density. This notion defies our understanding of matter, energy, and space, and remains one of the deepest unresolved questions in physics. Yet even if we cannot fully explain what happens at the singularity, its mathematical existence is essential. It defines the outermost boundary of space-time as we know it, a place beyond which observation and measurement are no longer possible. Black holes and their importance. Schwarzschild's black hole remained a theoretical construct for decades, an abstract solution dismissed by many scientists as having little bearing on the observable universe. But with the rise of modern astrophysics, black holes became far more than a mathematical curiosity. Today, black holes are recognized as central players in the evolution of stars and the structure of galaxies. In fact, it is now widely believed that nearly every large galaxy, including our own Milky Way, harbors a supermassive black hole at its core. Observational evidence. Throughout the 20th century, theoretical predictions about black holes began to find support in observational data. In the 1970s, X-ray telescopes detected intense emissions near certain stars, which were later identified as binary systems, a normal star orbiting a black hole. Matter drawn from the companion star formed a hot accretion disk around the black hole, emitting X-rays in the process. In 2015, the first direct detection of gravitational waves was made by the LIGO detectors, capturing the merger of two black holes. This confirmed a critical prediction of general relativity, that massive objects like black holes could collide and send ripples through spacetime. In 2019, the Event Horizon Telescope produced the first image of a black hole's event horizon, located in the center of galaxy M87, offering direct visual confirmation of its existence. These discoveries transformed black holes from theoretical ideas into observable and measurable phenomena. The role of black holes in the universe. Black holes are not merely endpoints of collapsed stars, they actively shape the universe. Galactic formation and growth. Supermassive black holes at the centers of galaxies influence star formation through their gravitational pull and energetic outflows. These emissions can regulate or even suppress the formation of new stars by heating or expelling surrounding gas and dust. Time dilation and warped spacetime. Near a black hole, the flow of time slows drastically. Clocks closer to the event horizon tick more slowly than those farther away, a phenomenon called gravitational time dilation. This effect, predicted by Einstein and confirmed in weaker gravitational fields, such as in satellite experiments, becomes extreme in the vicinity of a black hole. Conclusion: black holes and the edge of knowledge. The black hole solution revealed how spacetime could curve into a point of no return, and it marked the boundary where current physics begins to unravel. The singularity at a black hole's core suggests that a new theory is needed, one that can unite general relativity with quantum mechanics. Although black holes are a direct outcome of Einstein's equations, they remain among the most mysterious objects in the cosmos. They offer a unique window into the nature of space-time and provide an unparalleled testing ground for our understanding of gravity. What was once a speculative mathematical idea has become a powerful symbol of the deep, interconnected relationship between matter, energy, and the fabric of reality itself. Chapter 6: Gravitational Waves, the Ripples in Spacetime. In 1915, when Einstein developed general relativity, one of its most profound predictions was that massive objects, such as stars and black holes, could generate ripples in spacetime. These ripples, called gravitational waves, propagate outward from their source, much like waves spreading across the surface of a pond. The idea was revolutionary. Not only could mass distort spacetime, but it could also send dynamic disturbances through it. Yet these waves were expected to be extraordinarily faint, making their detection an immense challenge. Gravitational waves in theory. Gravitational waves arise from the acceleration of massive objects. When two such bodies, like black holes or neutron stars, orbit each other, they radiate energy in the form of space-time ripples. These waves travel at the speed of light, subtly stretching and compressing the space they move through. Einstein's equations predicted their unique effects. As a gravitational wave passes, it deforms spacetime by stretching and squeezing it. If such a wave were to pass through Earth, the distance between two fixed points would briefly expand and contract, with these changes occurring in perpendicular directions. But these effects are incredibly subtle, so small that for decades they seemed beyond the reach of measurement. The search for gravitational waves. For much of the 20th century, gravitational waves remained a theoretical concept. Though widely accepted, they lacked direct observational proof, until technological advancements finally made detection possible in the 21st century. The Laser Interferometer Gravitational Wave Observatory, LIGO, Struss was designed for this exact task. LIGO consists of two enormous L-shaped detectors located thousands of kilometers apart. Each arm of the detector spans several kilometers. As a gravitational wave passes through, it alters the length of these arms by a tiny amount, stretching one arm while compressing the other. Detecting such an incredibly small change, thousands of times smaller than the width of a proton, demanded extreme precision. But in 2015, LIGO achieved what many once thought impossible: the first detection. On September 14, 2015, LIGO recorded the first ever detection of a gravitational wave. This signal originated from the merger of two black holes, each roughly 30 times the mass of the Sun. As they spiraled inward and collided, they released gravitational waves that reached Earth and were picked up by LIGO as a distinct chirp, a rise in frequency and amplitude as the merger occurred. This discovery was a landmark for general relativity, directly confirming Einstein's century-old prediction. More than that, it unveiled a way to observe some of the universe's most extreme and hidden events, the mergers of black holes. The implications of gravitational waves. Detecting gravitational waves opened an entirely new window into the cosmos. These waves carry rich information about their origins, such as black hole masses, spins, and dynamics, which can't be accessed through traditional electromagnetic observations like visible light or radio waves. The implications are profound. 1. Testing general relativity. Gravitational waves allow precise tests of Einstein's theory in strong field conditions. Their propagation, frequency, and amplitude match general relativity's predictions for merging black holes with extraordinary accuracy. 2. Observing black hole mergers. Gravitational waves offer a direct method to observe cataclysmic events such as black hole and neutron star collisions. These events often emit no light, making them invisible to standard telescopes, but they resonate clearly in spacetime. 3. Expanding our understanding of the universe. These waves come from regions of space and epochs of time that are otherwise hidden. They enable scientists to explore the universe from a new perspective, filling gaps in our knowledge of the most energetic and distant cosmic events. The future of gravitational wave astronomy. The discovery marked the birth of gravitational wave astronomy, a transformative approach to exploring the cosmos. As detectors grow more sensitive, many new discoveries await. Merging neutron stars. These can reveal details about the ultra-dense matter inside neutron stars, probing physics beyond what Earth-based experiments can reach. Binary systems. Continued observations of binary black holes and neutron stars will sharpen measurements of their properties, helping refine models of how stars live and die. The early universe. Researchers hope to detect gravitational waves from the early universe, perhaps even from cosmic inflation or the Big Bang itself, offering insights into the very origin of spacetime. The path ahead is full of promise. What we've observed so far is just the beginning of this new way of listening to the universe. The detection of gravitational waves stands as a powerful confirmation of general relativity, tangible proof that massive bodies truly do send ripples through spacetime. These waves have become a new kind of cosmic messenger, allowing us to study extreme environments and cataclysmic events that were once out of reach. In many ways, gravitational wave astronomy marks the opening of a new frontier, one where Einstein's legacy continues to light the way as we journey deeper into the structure of reality itself. Chapter 7. Cosmology. The expanding 20th century, general relativity transformed our view of space-time, though its broader consequences took time to unfold. One of the most profound applications emerged when scientists began applying Einstein's equations to the cosmos itself. This led to a revolutionary new understanding of the universe's structure and its evolution. The most significant breakthrough in cosmology came directly from Einstein's equations. They implied a universe that was not static, but either expanding or contracting. This insight marked the beginning of modern cosmology. The Einstein field equations and the universe. When applied on a cosmic scale, Einstein's equations enabled scientists to model the large-scale structure of spacetime. These equations accounted for the overall distribution of matter and energy, offering a powerful framework for understanding the universe's behavior on its grandest scales. At the time, astronomers believed the universe to be homogeneous and isotropic, appearing the same in all directions and locations. To accommodate this idea within his equations, Einstein introduced the cosmological constant, which allowed for a static and unchanging universe. This seemed to match observations, but only briefly. The discovery of an expanding universe. In 1929, Edwin Hubble made a discovery that reshaped our cosmic understanding. The universe is expanding. He found that galaxies were receding from us, and the farther away a galaxy was, the faster it appeared to move. This relationship became known as Hubble's law. Hubble's observation upended the static universe model. The expansion wasn't confined to any one region. It was the fabric of spacetime itself stretching out, just as Einstein's equations had predicted. With this, the universe was no longer a fixed backdrop, but a dynamic and evolving entity. Einstein quickly abandoned the cosmological constant, recognizing it was unnecessary in an expanding universe. The Big Bang and the origin of the universe. The discovery of the universe's expansion pointed to a singular beginning, a moment in the distant past when the universe was infinitely small, dense, and hot. This idea became the foundation of the Big Bang theory. According to general relativity, this initial singularity marked the birth of space and time itself, with the universe expanding from that moment onward. Further support for the Big Bang theory came in 1965, when Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation. This faint glow is the residual heat from the early universe, offering a glimpse into the cosmos just 380,000 years after the Big Bang. The discovery confirmed that the universe did, in fact, begin in a hot, dense state and has been expanding ever since. The curvature of space-time and the shape of the universe. Einstein's field equations also provided a way to describe the universe's shape, determined by the total amount of matter and energy it contains. The curvature of spacetime defines three possible scenarios. Closed universe, with positive curvature like the surface of a sphere. Such a universe would eventually stop expanding and collapse back into a singularity. Flat universe. With zero curvature, it would continue expanding forever at a steady rate. Open universe. With negative curvature, it would also expand forever, but more slowly over time. In the late 1990s, astronomers studying distant supernovae made a surprising discovery. The universe's expansion is accelerating. This unexpected result led to the hypothesis of dark energy, a mysterious form of energy that now appears to account for about 70% of the universe's total energy. Dark energy exerts a repulsive force that opposes gravity, causing the expansion of space to speed up. The fate of the universe, understanding the curvature and expansion of the universe, leads to deep questions about its ultimate fate. Several scenarios are possible. Big freeze. If expansion continues indefinitely, stars will eventually burn out, galaxies will drift apart, and the universe will become dark and cold. Big crunch. If expansion reverses, the universe could collapse back in on itself in a final crunch. Big rip. If dark energy becomes increasingly dominant, it could tear apart galaxies, stars, and even atoms, ripping the universe apart. General relativity is the cornerstone of modern cosmology. It enables us to model the dynamics of the universe as a whole, predict phenomena such as black holes, gravitational waves, and cosmic expansion, analyze the formation and evolution of galaxies and clusters on a grand scale. Without general relativity, the concept of space-time as a dynamic, evolving fabric would not exist. Its insights into the large-scale behavior of the universe have made it essential to understanding the cosmos. Conclusion: a new perspective on the universe. General relativity has profoundly reshaped our view of the universe. What was once thought to be static and eternal is now seen as dynamic and ever-changing. The discoveries of cosmic expansion, dark energy, and space-time curvature all rest on the framework Einstein created. As we continue to probe the origins, structure, and fate of the universe, general relativity remains our guiding theory, revealing that matter, energy, space, and time are inextricably woven into the fabric of a living cosmos. Chapter 8: Interstellar. General Relativity in Story and Emotion. Interstellar is more than science fiction. It is a cinematic meditation on time, gravity, and the limits of human perception. A narrative built not around futuristic gadgets, but around the very structure of spacetime itself. Here, general relativity isn't merely part of the setting, it is the substance of the story. One of the most compelling demonstrations of Einstein's theory appears in the film's depiction of time dilation. On Miller's planet, which orbits close to the massive black hole Gargantua, the gravitational field is so intense that time itself slows dramatically. While the crew spends just over 3 hours on the planet's surface, 23 Earth years pass for their colleague waiting in orbit. The consequences are not merely technical, they're emotional. One crew member watches a lifetime go by in isolation. Another returns to find his children grown and estranged. This is not poetic exaggeration. This is physics, portrayed with startling clarity. Time dilation near a massive body is one of general relativity's most striking predictions, made real through the emotional cost of exploration. The black hole itself, Gargantua, is rendered with scientific rigor. The swirling ring of light around its shadow is not a flourish of imagination, but a visual representation of gravitational lensing, light bent by the black hole's immense curvature of space-time. Developed using equations provided by physicist Kip Thorne, the image of Gargantua brought real scientific insight even as it served the story. It becomes a character of its own, powerful, enigmatic, and a doorway to the unknown. The climax of the film explores one of the most speculative and philosophically rich ideas in modern theoretical physics, the possibility of higher dimensions. As Cooper plunges into the black hole, he is not crushed by singularity. Instead, he enters a higher dimensional construct, a tesseract, built by an advanced intelligence that perceives time as a physical dimension. Here, time is no longer linear. It becomes a landscape that Cooper can move through. He witnesses moments from his daughter's childhood as if walking through a corridor of memory, able to influence the past through gravitational signals. This visual and narrative leap is inspired by the concept of the block universe, a four-dimensional spacetime where all events, past, present, and future, exist simultaneously. In this view, time does not flow. Instead, our perception moves through it. General relativity allows this interpretation. Time is just another dimension, affected by mass and motion, woven together with space into a single fabric. In Interstellar, this idea is dramatized with emotional urgency. Time is not just a coordinate, it is a medium for connection, loss, and hope. The film also takes a bold thematic step in suggesting that human emotion, especially love, might have its own kind of force. While speculative from a physics standpoint, this metaphor serves to underline the core message, that even in a cold, deterministic universe shaped by the geometry of spacetime, meaning still emerges from our subjective experiences. The intangible becomes a guidepost. What matters to us personally transcends even the distances between stars. At the heart of the story lies a loop of causality. Cooper becomes the very source of the mysterious signals that once guided him. The sender and the receiver are the same. Though counterintuitive, such a narrative twist is not outside the bounds of physics. Certain solutions to Einstein's field equations, such as those involving rotating universes or wormholes, allow for closed time-like curves, paths through spacetime that loop back on themselves. These remain theoretical, but they remind us that the universe may not be limited by the linear logic of everyday experience. Interstellar succeeds because it refuses to separate science from human experience. It transforms the abstractions of general relativity, curved spacetime, time dilation, singularities, into visceral realities. It asks what it means to be human when time can stretch or collapse, when the distances between moments become as vast as galaxies, and when causality itself can fold in upon itself. In the end, general relativity is not just about equations. It's about understanding the architecture of reality. It tells us that time and space are dynamic, malleable, and deeply interconnected. Interstellar brings this understanding to life, not with a blackboard but with a story, one in which science is not merely a tool, but a language for expressing longing, sacrifice, and hope. Where Einstein gave us the mathematics, Interstellar gives us the emotion. It is a story where science does not stand apart from the human experience, but deepens it. And in doing so, it shows us what it means to live, love, and strive within a universe that is far stranger and far more beautiful than we ever imagined. And so we arrive at the end of our journey, a journey through curved spacetime, through the minds of those who dared to rethink the universe, and through the deep logic that binds gravity to geometry. The general theory of relativity is more than a scientific milestone. It is a new way of seeing, a lens through which the universe reveals its silent, elegant structure. From falling apples to orbiting stars, from the warping of time to the collapse of matter into singularities, Einstein's insight reshaped our place in the cosmos. Yet even now, over a century later, relativity continues to challenge us, not just to understand more, but to imagine deeper. The theory remains unfinished in spirit, always reaching toward whatever lies just beyond the horizon. Perhaps that is its greatest legacy, not in the answers it gave, but in the doors it opened, to discovery, to wonder, and to the infinite geometry of the unknown.